Today we will begin answering the question, what is sound? And we will define some of the basic concepts of sound. First, a textbook definition. Sound is produced when an object vibrates and causes the surrounding air to move. So what does this look like? Let's start with a sound source. When that source vibrates, it causes the air molecules around it to vibrate, creating a wave that emanates from that center point in all directions. Because the molecules are vibrating, there are areas where the molecules are closer together and areas where they are farther apart. The areas where the molecules are closer together are higher pressure, or compression, while the areas where they are farther apart are lower pressure or rarefaction. In this illustration, the darker areas of the line moving from the sound source represent the areas of compression or high pressure, and the lighter sections represent the areas of rarefaction or low pressure. Sound travels away from the source, but the air molecules just move back and forth, bouncing into each other, causing the sound to move away from the source as the molecules bounce into each other. Although sound moves laterally or longitudinally away from the source, we often show the movement with a transverse waveform, which moves above and below a center line, at which point the molecules are at an equilibrium or neutral point. The points on the waveform reflect the pressure at that moment in time. When the point is above the center line, the pressure is higher or compressed. And when the point is below the center line, the pressure is lower or rarefied. Using the diagram in the upper right corner, the black line represents a vibrating sound source. As it moves to the right, it compresses the air molecules, causing them to move closer together and move to the right. As the source moves to the left, the air molecules are spread apart or rarefied. Although the movement of the molecules is like two people with a spring on a flat surface with one person pushing their end of the spring closer and further from the other person, we visually show the movement of the molecules with a line that moves up and down through the center equilibrium line, as seen in these two illustrations. Sounds around us comprise very complex combinations of vibrations, allowing us to distinguish between different objects or people. For this part of the course, we will use the basic sine wave for most of our demonstrations, since it is easy to visualize. One of the best ways to visualize a sine wave is to think of a pendulum, a weight suspended on a string swinging back and forth. Another way to think of a sine wave is the point of a circle stretched over time. A sine wave has a very pure sound since it consists of a single frequency, and they are often called pure tones. There are 5 characteristics used to describe basic sound waves. Sound at standard atmospheric pressure and temperature travels at 1130 feet per second. A lowercase letter c represents the speed of sound. The loudness of sound is called amplitude, and it represents the maximum displacement of the air molecules from the equilibrium point. A capital A represents loudness, and the units are typically decibels, or the letters dB. The period is the time for one cycle of the pressure wave to pass a stationary point. The equation for the period is 1 divided by the frequency and is represented by a capital T and expressed in seconds. The wavelength is the length of one complete cycle. The wavelength is the speed of sound divided by the frequency, represented by the Greek letter lambda and measured in feet. And finally, the frequency is the number of waves, or cycles, to pass a stationary point in 1 second. Frequency is measured in cycles per second, or hertz, and it is 1 divided by the period, represented by a lowercase f. To show how to use these equations, we will answer the following questions. What is the frequency if 500 waves pass by in 1 second? What is the wavelength of a 500 hertz wave? If you see lightning, then you hear thunder 5 seconds later. How far away from you was the lightning? For the first question, we are given 500 cycles in 1 second. This is the direct definition of the frequency. So 500 cycles per second is the frequency, and the units are hertz, or 500 hertz. For the second question, we must solve for the wavelength, or lambda, which is the speed of sound divided by the frequency, or 1130 feet per second divided by 500 hertz, giving us a wavelength of 2.26 feet. The final question is important to us Since we live in the lightning strike capital of the world, since light travels instantaneously from one point to another, it is not a factor in this question. In this case, sound travels 1130 feet per second, and the thunder takes 5 seconds to get to us. So we multiply 1130 feet per second by 5 seconds, giving us 5,650 feet, or just over a mile. Most of this course will focus on sounds within the human hearing range. The audio spectrum, or audible range of human hearing, is accepted to be between 20 and 20,000 hertz, or 20 kilohertz. Our hearing is typically the most sensitive between the frequencies of 150 hertz to 5,000 hertz. Sounds below the human audible range are called infrasound. If infrasounds are loud enough, although we won't hear them, our bodies and nervous system will detect them as vibrations, while sounds above the human audible range are called ultrasound. Sounds between about 20 to 40 kilohertz are not audible to humans, but we sometimes feel them as pressure or congestion. Most sounds are a complex combination of vibrations called complex waveforms. If the complex waveform repeats itself at regular intervals, probably with only slight variations, it is considered to have a pitch or central frequency. If a complex waveform is highly random and has little or no discernible pattern, it is called noise. The process of breaking complex waveforms into their component sine waves is called Fourier analysis. Conversely, combining harmonically related sine waves into a complex waveform is called Fourier synthesis. Each harmonic frequency is mathematically related to the fundamental frequency. If the harmonic frequency is higher than the fundamental frequency, it is called an overtone. If the harmonic frequency is lower, it is a differential harmonic. Harmonic overtones are related to the fundamental frequency through multiplication factors. For example, the fundamental or base frequency is also called the first harmonic. To calculate the frequency of the different harmonics, simply multiply the fundamental frequency by the number of the harmonic. On this table, the fundamental frequency is 55 hertz, so the first harmonic is 55 hertz times 1, or 55 hertz. The second harmonic is 55 hertz times 2, or 110 hertz. The eighth harmonic is 55 hertz times 8, or 440 hertz. The third column of the table relates the harmonic overtones to their musical relationships. The fundamental is the starting note. If you double the frequency, you have the second harmonic. The note is 1 octave above the fundamental. When you double the frequency again, you have the fourth harmonic. You have a note 2 octaves above the fundamental. Going back to the third harmonic, it is 3 times the fundamental and is musically a fifth above the first octave. Harmonic overtones can be combined mathematically to create additional complex waveforms through a process called Fourier synthesis. Some simple examples are shown here as square, triangle, and sawtooth waveforms. First, we see the singular sine waveform, which is simply the fundamental frequency. In the second example, we see a square waveform, which is made up of the fundamental frequency plus 1/3 times the third harmonic, plus 1/5 times the fifth harmonic, etc. In contrast, the sawtooth waveform at the bottom includes all the harmonics, not just the odd ones of the square wave. Pause the video and check out the link at the bottom to experiment with an additive synthesis waveform generator.
An important component of sound design is gaining an understanding of how harmonics and overtones work. So for an example, let's take a look at 2 common orchestral instruments, the clarinet from the woodwind family and the trumpet from the brass family, and take a look at how they differ in harmonic content. First, here's a clarinet playing an A440. Now, if I freeze that there, we can take a look at the fundamental frequency very clearly coming through at 440 hertz. We also can see the 880 hertz, the 1320, and so on. So the fundamental 440 hertz times 1 times 2, times 3, times 4, times 5. Very predictable pattern here, all working to reinforce this fundamental A440 pitch. It's only when these overtones end up being slightly off or very off from that mathematical relationship do we start losing a sense of a pitch center, and we have what are more characterized as overtones and not harmonics. In the case of harmonics, this would be called the fundamental or harmonic 1, harmonic 2, harmonic 3, harmonic 4, etc. We could also call these overtones, they are harmonic overtones, and in this case we have the fundamental, the first overtone, the second overtone, the third overtone, etc. Another characteristic to pay attention to here with the clarinet, even though all of the harmonics that we would predict are present, we do notice that rather than a smooth attenuation that we might expect, we notice that the second harmonic or the first overtone drops down a little bit, and then the third harmonic, which should be a bit lower, actually pops up again. And we have kind of a back and forth a little bit here where the odd harmonics, somewhat like a square wave, tend to have a little bit more emphasis, at least early on, than do the even harmonics. And that's a characteristic of a cylindrical shaped instrument like a clarinet. By contrast, a conical shaped instrument like a trumpet is going to have a lot more intensity in all of the harmonics and a more even distribution of each of the harmonics in the series. So let's take a look at that. Okay, so a very similar pattern in terms of having the 440 hertz, 880, 1320, and so on, but there's much greater intensity with the overtones, particularly in this area where you see that the harmonics are much more intense compared to what we saw with the clarinet. So this is typical of, as I say, a conical shaped instrument like a trombone, meaning that where the mouthpiece is the smallest diameter of the horn, and as you get out towards the bell, it flares out further and further, creating more of a density of overtones, giving that bright quality that we expect from brass instruments.
While harmonic overtones are mathematical multiples of the fundamental frequency, differential harmonics are the resulting frequency when two or more waveforms with similar amplitudes and frequencies are subtracted. The resulting frequency is a phantom tone that does not actually exist, but our ears and brains create the frequency. As an example, if we play a 1 kilohertz tone and a 1.2 kilohertz tone separately, you hear each tone. When played together, you hear the two tones, as well as the differential frequency between the two of 200 hertz. Similarly, but more noticeably, when two tones that are only 5 hertz apart or 2 hertz apart are played, the differential harmonic is more pronounced. The differential harmonic relationship is how stringed instrument musicians, such as guitarists, tune their instruments. Instruments that use their body as the sound-generating surface, such as bells, cymbals, marimbas, and xylophones, produce in harmonic overtones, and they do not produce harmonic overtones. These instruments produce overtones that depart from the whole number multiples of the fundamental frequency, thus being inharmonic. These instruments almost always sound out of tune with themselves and other instruments.
All right, now let's take a look at an instrument that does not have a strong pitch center. What we should see is a series of overtones that do not make integer ratios with the fundamental frequency like we saw with the clarinet and the trumpet. In other words, if a pitched instrument is being analyzed, we'll see the fundamental an octave above that, which would be 2 times the frequency of the fundamental, then 3 times, 4 times, 5 times, etc. This isn't a go-go. It's an instrument that we describe in Chapter 2. Let's take a look at it. All right, so what we see in our spectrum analysis here is we have a fundamental frequency of around 1077 hertz. So what we should predict for the first overtone would be in the vicinity of 2154, somewhere in that territory. And when we come up here, we're a little bit off from that. We're in that ballpark, but not quite precisely, and it needs to be really precise in order to reinforce that pitch. The same thing we notice as we continue along here with the dominant overtones not having an integer relationship with the fundamental. The result is there is a quality of pitch to the sound, but it's not a type of pitch you could hum along to. It's not a pitch that you could easily identify. So there could be a higher and lower, but it's hard to describe this as being a certain pitch on the musical scale. By contrast, let me clear this and let's take a look at instead a flute playing an A440. So like the clarinet and trumpet we saw before, here's the dominant 440 Hz fundamental, the first overtone at 880 Hz, the second overtone or the third harmonic up here at 1320 Hz. So very clearly reinforcing the fundamental pitch with a percussion instrument with its overtones, not so much the case.
Non-repetitive sounds are known as noise. Non-repetitive waveforms do not have a recognizable pitch and they sound noise-like. The frequency content of a noise source is usually a collection of unrelated frequencies. In the audio industry, we primarily use 3 different colors of noise: white, pink, and brown, although there are many other colors. White noise is described as equal energy or amplitude per frequency and sounds similar to a waterfall. Pink noise is filtered white noise that gets quieter by 3 decibels per octave, therefore having equal energy per octave versus frequency. This sounds like a light to moderate rainfall. Brown noise, rarely used in audio engineering, is filtered by 6 decibels per octave and sounds more like the low rumble of ocean waves during a storm. Finally, there is black noise, which is silence. Complex waveforms are created by electronic instruments, such as synthesizers using harmonic filtering or summing processes to create harmonically rich sounds. Fourier synthesis is summing 2 or more sine waves to create a complex waveform. Additive synthesis is like Fourier synthesis, but is the summing of 2 or more complex waveforms to form a new waveform. Frequency modulation synthesis sums sine waves in equal frequency distributions to form a new waveform using differential harmonics. Subtractive synthesis removes or reduces harmonics using complex filtering to create new waveforms. And formant synthesis manipulates the formant to change a waveform into a different sound. We will learn more about formants in a future lecture.